This video is on the first quantization of the free bosonic string via the covariant Dirac method, sometimes called the old covariant method. However, before we get to quantization, we must sort out a classical description of the string first. The most obvious way to describe a string is with a space-time vector, x mu of sigma and tau, that points at the location of a particular point along the string, the coordinate sigma, at a particular point in time, specified by the parameter tau. If one can find x mu for all sigma and tau, then the string world sheet is completely specified and the classical dynamics of the string are completely understood. This is the natural generalization of using a similar vector to give the location of a point particle at a given time as done in ordinary mechanics. Knowing this vector for all tau completely specifies a particle's world line. Also extending ideas from point particle theory, one might guess that the action of a string's position vector would be proportional to the area of the world sheet on account of the fact that the usual point particle action is proportional to the length of the particle's world line. As we will see, this, or more specifically a classical equivalence of this, turns out to yield a perfectly valid quantum theory with very interesting properties. Let's figure out how to write such an action. First, note the following. An infinitesimal displacement on the world sheet like this corresponds to this change in the background space-time position. The distance of the displacement squared, therefore, is this. Thus, the metric of the world sheet, usually called the metric induced on the world sheet, simply takes this form. With this knowledge, we are ready to write an action explicitly for x mu, which is proportional to the area of the world sheet. Specifically, given how volume elements work, we have the Nambu-Gatto action. The proportionality constant 1 over 2 pi alpha prime is written this way in accordance with convention. The only quantity associated with a string that has the right dimensions to be this proportionality constant is the string tension. The string tension serves as the string analogue of the mass, which multiplies the analogous point particle action. This actually makes a lot of sense when you consider the static case. In the static case, the integral just measures the string length, but also the kinetic term zeroes out, and the Hamiltonian simply becomes minus the Lagrangian. Therefore, the string tension is the proportionality constant between the energy and the string length. As a result, it is the energy/mass per unit length of the string. Before we move on, it's important to note the symmetries that this action has. To start with, it is manifestly space-time rigid Poincare invariant. Perhaps less obviously, it is also world sheet reparameterization invariant. The quick way to explain this is to reference knowledge of general relativity. The Einstein-Hilbert action obtains its invariance under general coordinate transformations via the inclusion of the √-g factor. Transforming as a scalar density, it compensates for the general coordinate transformation property of the volume element. Similarly, in the Nambu-Gatto action, we have the square root of minus the determinant of a tensor, which therefore also transforms like a scalar density under reparameterization, thus compensating for the transformation of the world sheet area element. One can also show that the Lagrangian density does transform like a scalar density by using the chain rule to write this string of mathematics. Carrying on. Based on the fact that the string position vector components are world sheet scalars, one might also attempt to describe the string by writing a scalar field Lagrangian for them in world sheet space. If we employ the tensor calculus techniques familiar from general relativity, we can even write one that is manifestly world sheet reparameterization invariant. Specifically, we have the Polyakov action. In addition to the reparameterization invariance, we can see that it's also manifestly space-time rigid Poincare invariant, as with the Nambu-Gatto action. Beyond this, we have that the Polyakov action is non-trivially Weyl invariant. The Nambu-Gatto action is trivially invariant under this transformation because it includes only x mu, which doesn't transform. The big question is, which action do we select? It turns out that they are classically equivalent. We will show this and then select the second action because it's easier to quantize. At least it's easier to quantize in a covariant manner. And we will find that it yields a perfectly acceptable quantum theory. The classical equivalence doesn't necessarily mean that directly quantizing both actions would yield exactly the same quantum theory, but this option is a convenient pathway to a quantum theory that both works and yields either theory in the classical limit because they're classically equivalent. In that sense, sense, we will be finding a valid quantum version of both classical theories, including the more intuitive Nambu-Gatto action. Anyway, now on to proving that they are classically equivalent. To do this, we must first calculate the equations of motion for the Polyakov action. Much like with general relativity, it's easiest to do this via direct variation. I will start by varying the action with respect to the worldsheet metric, assuming that its variation vanishes at tau initial and tau final. Making the variation explicitly with respect to the metric gives us this. Next, product ruling it and simplifying leaves us with the need to calculate a determinant variation. Fortunately, there is a formula for differentiating determinants that we can apply. So in the context of the metric, we have this. If we remember some of what we know about the metric, we see that we have this. Next, there is a rule about differentiating inverse matrices. We can manipulate this productively. Therefore, we are finally left with this. Inserting and simplifying is then straightforward. If the integral is 0, the integrand is 0 in any context where the integration limits tau I and tau f are arbitrary, and the selected range, and therefore integration limits of sigma, are an arbitrary convention. Therefore, we have this. We also need it to be true for arbitrary variations, so the equation of motion is this. The left-hand side is recognizable as the energy-momentum tensor from the worldsheet perspective for the d, as in space-time dimension, worldsheet scalars and x mu. Given that the action contains nothing else, we're safe to interpret this equation of motion as the statement that the energy-momentum tensor living on the worldsheet is classically 0. That's not to suggest that the energy-momentum tensor of a string moving in space-time is 0. Now, continuing on with our effort to show the classical equivalence of the Polyakov and Nambu-Gatto actions, we must solve this equation for the metric. Then, thinking about how a 2x2 determinant works, we can easily write this. We therefore have this key identity. Inserting this into the Polyakov action gives the Nambu-Gatto action, so they are classically equivalent. For future use, we must also calculate the Polyakov equation of motion for x mu. Here we must take the variations to be 0 at t initial and t final, and at the endpoints to get the usual equations of motion, which are a and pi, where a equals 0 for the open string and minus pi for the closed string. Initially, the algebra is pretty straightforward. Leveraging the fact that both metrics are symmetric to do some index juggling gives us this. Next, integration by parts gets us here, where the boundary term for the sigma part of the integration vanishes for both open and closed string cases because we take delta x rho to vanish at tau initial and tau final. The tau integral boundary term vanishes for the closed string because x mu of tau and minus pi equals x mu of tau and pi. However, for the open string, setting it to be 0, which is the normal thing to do, gives, with index juggling, this non-trivial boundary condition, which is the usual open string boundary condition. Either way, we're left with the following variation. If the integral is 0, the integrand is 0 in any context where the integration limits are arbitrary. Tau initial and tau final are arbitrary, and the selected range for sigma is an arbitrary convention, so we find this. We also need it to be true for arbitrary variations, so with some index juggling, the equation of motion is this. Given the square root in the Nambu-Gatto action, it isn't particularly easy to deal with, at least when covariant quantizing. So as explained previously, we will therefore select the Polyakov action as we set up for quantization. It isn't immediately obvious how this helps because the Polyakov action and its equation of motion for x mu still aren't very simple. However, it turns out that we can make a gauge choice that will simplify things considerably. Being a two-dimensional symmetric second-rank tensor, the worldsheet metric has 3 degrees of freedom to start with, but we also have reparameterization invariance across 2 coordinates. We therefore expect to be able to remove up to 2 degrees of freedom by fixing the gauge. Quite conveniently, there's a theorem from mathematics that provides a good way to do this. Specifically, for a two-dimensional smooth space, it can be proven that there is always a coordinate system in which the metric/line element takes on the following form. Selecting this form for the metric therefore represents a valid way to fix the reparameterization gauge to the effect of lowering the number of metric degrees of freedom from 3 to 1. and this particular selection is useful because it simplifies the relatively complicated Polyakov theory. To start with, the x mu equation of motion reduces to the familiar wave equation. The other equation of motion doesn't simplify down nearly as much. However, the open string boundary condition does simplify down considerably. Also, we can clearly see that the gauge-fixed x mu equation of motion follows straightforwardly from the Polyakov action under the same gauge constraint. Because the worldsheet metric is no longer a variable field, we have to just take the TAB equals 0 constraint as a given when using this simplified action. Now, before we move on to quantization, I want to take a moment to compute the canonical momentum and the Poisson brackets for the xp phase coordinates, because we will need them later and there really is no more convenient place to put this part of the calculation. First, the canonical momentum works out to be this. And now for the xp phase space coordinate Poisson brackets, which are so important for the Dirac method. The usual definition of the Poisson bracket is this. If we use the Einstein summation convention, then the natural generalization of this formula to the string variables looks like this. Notice that the discrete index sum is not shown because of the summation convention, and the integral is necessary to sum over the continuous index sigma tilde. When I don't denote the tau dependence, assume the whole expression is at equal time. Evaluating this proceeds like this, and the other two cases vanish trivially. To summarize, we have these results. At this point, we will need to specialize to either the open string or the closed string, because the rest of the discussion will be boundary condition dependent. Also, we will handle all of the work required to prepare for quantization for the closed string first and then do the same for the open string. We will then work through the quantization of the open string and then do the same for the closed string. This might seem like a strange way to order the work, but it's the easiest way to introduce everything. Okay, on to preparing the closed string for quantization. Given that we usually choose the sigma range of the closed string to be negative pi less than or equal to sigma less than pi and require it to be continuous everywhere, i.e. satisfy these boundary conditions, we are free to Fourier expand x mu of tau and sigma as follows, where x negative n equals the complex conjugate of xn because x mu is real. The canonical momentum and total canonical momentum become these. The alpha formulas will make sense later when we introduce those quantities. If we then apply the equations of motion to this, we find this equation, which is just the equation of motion of a simple harmonic oscillator. And if we insert this expansion into the gauge-fixed action, we find this action. From our knowledge of simple mechanics, we know that the Hamiltonian for a simple Lagrangian like the one under this action integral will just be different by the sign of the potential term. Therefore, written in xp variables in the original constant, we have this Hamiltonian, which, given that x negative n equals the complex conjugate of xn, and therefore the same is true for p negative n, is just the Lagrangian / Hamiltonian of the complex generalization of an infinite set of simple harmonic oscillators. Therefore, through this Fourier expansion, we can see that the classical string problem can be broken down into an infinite collection of simple harmonic oscillators. This is actually really good news because this means that the process of quantizing the string can be reduced to that of quantizing simple harmonic oscillators, which is one of the easiest and most familiar problems in quantum theory. Arguably, the easiest and most useful way to quantize the simple harmonic oscillator is to use Dirac's famous raising and lowering operator technique as a convenient reparameterization as we apply the broader Dirac method for quantizing systems with constraints. To remind you, this technique consists of first reparameterizing the quantum harmonic oscillator Hamiltonian with these new variables, which satisfy this commutation relation, at which point the Schrödinger equation becomes this. By then applying this Hamiltonian to the energy eigenstates that have already been acted on by A and A dagger operators, we can show using their commutation relation that the resulting states are also energy eigenstates, but with increased or decreased energy, isospectrally, for A dagger and A respectively, revealing them to be raising and lowering operators. We can then argue the existence of a vacuum satisfying this equation, which implies this position space differential equation, which can in turn easily be solved for the ground state wave function that, when normalized, works out to be this. We can also show that this operator just counts the number of energy quanta in a given energy eigenstate. It's called the number operator. Repeated application of the raising operator can then be used to construct the wave functions of the rest of the energy eigenstates, which ultimately yields this normalized result for the position space energy eigenfunctions and eigenvalues. Since we've broken the string down into a set of simple harmonic oscillators, the same quantization applies to them. We'll use an extremely similar reparameterization that works the same way. It turns out that in generalizing this raising and lowering operator method to the string, people don't usually adopt exactly the same definitions of A and A dagger. This is simply because the most mathematically convenient definitions are scaled slightly differently. If for a moment we define n to be a positive integer, the standard string theory parameters are these. Or if we stick to letting n go from negative infinity to positive infinity, they can be written like this, where we can see that the soon-to-be raising operators are just the alpha quantities for negative n, and the soon-to-be lowering operators are simply the alpha quantities for positive n. We will handle the case of n equals 0 as we go. Now I say soon-to-be because we haven't actually quantized yet. The alpha quantities so far are just a reparameterization. Notice how we can construct up to two independent sets of what will become raising and lowering operators with the existing variables of the closed string. The fact that up to two sets can be constructed tells us that it actually takes two distinct infinite sets of quantum harmonic oscillators to describe the closed string. Later on, we'll see that these independent sets are associated with the right and left moving sectors of the closed string. We will see that the open string can be described by only one such set because, given the different boundary conditions, which reflect that the ends aren't connected, there's only one set of standing waves rather than two. We will now verify that the alpha quantities we have defined do in fact satisfy the required Poisson bracket relations to become raising and lowering operators upon quantization. The easiest way to do this is to actually work with the Fourier sum of the alphas, specifically these quantities. We can easily calculate the Poisson bracket relations of script p mu and script p mu bar from the ones we already have, and then use those to calculate the alpha Poisson brackets. First, script p mu with itself. We can use the Poisson bracket identities to expand this out. We then see that the third term is 0 from the fundamental Poisson bracket for p mu with itself. Evaluating the others requires differentiation of the other fundamental Poisson brackets. Inserting all of these yields this. Next, we have script p mu bar with itself, which proceeds similarly to the one with script p mu. And finally, script p mu and script p nu bar works out like this. To summarize, we have these Poisson brackets, and now we can calculate the alpha Poisson bracket relations from these. Let's start by inverting the alpha-based formulas for script p mu and script p mu bar. Standard Fourier theory tells us that the inverted expressions are these. First, the calculation of alpha n with itself, where I've suppressed the tau dependence. Inserting, simplifying, and substituting gets us here. We can handle the delta function derivative with integration by parts, where periodicity means the boundary terms vanish. Taking the derivative and performing the integrations gets our final answer. Next, the Poisson bracket for alpha n bar with itself works out similarly. And finally, the Poisson bracket for alpha n and alpha m bar vanishes more or less trivially. To summarize, we have these relations. If we now remember which are supposed to become raising operators and which are supposed to become lowering operators upon quantization, we can see, by comparison to the standard problem, that they do satisfy the correct Poisson bracket relations if scaled differently with the negative I and the n, for this to happen when exchanged for commutators. Of course, this assumes that the Hamiltonian has the usual form when expressed in terms of the raising and lowering operators. We'll find out that this is the case when we quantize and re-express the the Hamiltonian that way. Now at this point you may be thinking the following. With the action simply being that for d scalar fields and the x mu equation of motion turning out to be simply the wave equation, it seems obvious to then construct a quantum theory by applying ordinary canonical quantization, as one often does to quantize free scalar fields. Why do this weird thing where we relate the string back to the simple harmonic oscillator? The answer is somewhat long-winded and basically pedagogical, but it does contain quite a bit of useful insight, so we'll go through that before we continue with the Dirac method quantization of our system. First, a review of ordinary canonical quantization. It consists of solving the equation of motion for a general solution in terms of plane waves, and then quantizing these solutions by imposing the equal time commutation relations. One then inverts the solutions, solves for the Fourier coefficients, and then calculates their commutation relations. Following experimentation with their application to energy eigenstates, one finds that the Fourier coefficients behave like creation and annihilation operators, and one can therefore use them to construct the entire space of states of the theory. This approach basically amounts to reparametrizing the phase space using a solution to the equations of motion that we suspect will yield a convenient creation and annihilation operator description of the quantum theory. However, while we know that quantum fields must satisfy the classical equation of motion, we can't in general expect to be able to quantize a theory by first solving the classical equations of motion and then using the Fourier coefficients as variables in the quantum theory. There's simply no physical principle that guarantees this will work. It's just something that often does. To proceed more generally, we must reparametrize the phase space using a completely general, i.e. not constrained by the equations of motion, reparametrization first, including the Poisson brackets and the equations of motion, and then impose the equations of motion in the new variables. At this point, one is free to quantize. This avoids steps that are only justified by the fact that they happen to yield a consistent quantum theory in the end. As it happens, the usual canonical quantization would actually work out in this particular case, and this more careful alternative way will wind up simply generating the usual EOM solutions, as we will show. But for pedagogical reasons, we will follow this more general implementation of the Dirac method anyway. We are, however, welcome to take inspiration from how the shortcut method usually works out to make a guess at what kind of completely general reparametrization might lead to a raising and lowering operator description, and this is one way to motivate these formulas from earlier. On the left, we have a mode expansion that would normally show up in the common approach as a part of the initial solution to the equations of motion, in which the critical Fourier coefficients are first seen. And on the right, we have expressions that would normally show up as part of the inversion process used to solve for the Fourier coefficients. This is the inspiration we might take from the usual method, but notice that we are not assuming that the equations of motion are satisfied. We are only assuming a mode expansion that is valid for expanding any smooth function on such a finite space, making this completely non-restrictive and therefore a valid general reparametrization. We could then proceed to show that the Fourier coefficients do behave like raising and lowering operators, just like we do when quantizing a normal scalar field, revealing that we are taking enough inspiration from the ordinary canonical quantization to get the description we want from a completely general reparameterization. Unfortunately, I find this approach less clear than explicitly relating the string back to the simple harmonic oscillator problem, which is very clear, satisfying, and illuminating. So again, for pedagogical reasons, I did that instead. With that long-winded answer to the question of why not ordinary canonical quantization out of the way, we can get back to the raising and lowering operator reparametrized covariant Dirac method quantization of the string that we've been working on. To remind you, we'd finished computing the alpha Poisson brackets. The next steps in the Dirac method are to re-express the equations of motion in terms of these new variables, impose them, and then handle the constraints with another flurry of Poisson brackets. We will also derive an explicit expression for x mu in terms of the new variables just after imposing the equations of motion, because this provides some useful interpretive detail. First, we'll re-express the equations of motion. The easiest way to do this is to tau differentiate script p mu and script p mu bar, and then apply the existing equations of motion to get the new ones. Script p mu dot gives this, and script p mu bar dot gives us this. Solving them then gets us these formulas. Now we need to find that informative explicit expression for x mu. First, we have these expressions for script p mu and script p mu bar. We can then solve for x prime mu and then integrate with respect to sigma. A useful expression for the integration constant x naught mu can be found by solving the original harmonic oscillator equation. So we have this solution. This solution can be conveniently written in terms of separate left-moving and right-moving parts. As you can see, these manifestly are solutions to the original x mu equation of motion, the wave equation. You can also see that the alpha n quantities describe the left-moving sector of the closed string and alpha n bar the right-moving sector. Since we already know that they behave like raising and lowering operators upon quantization, we see that they can be interpreted as exciting and de-exciting their respective sectors of the closed string. At this point, we're ready to compute the Poisson brackets of the constraints, which is at the heart of the Dirac method. Before we can get exactly to that calculation, we need to re-express the constraints in a convenient and standard way. The form that we'll use is a convenient choice, primarily because of the algebra that they satisfy under Poisson brackets and eventually commutators. To remind you, the constraints we need to impose are these. There are actually only two distinct constraints here because TAB only has two distinct components, specifically these two. From these constraints, we can prove that script p squared and script p bar squared vanish. By doing this, we've traded our original two independent equations for two other independent equations, which the original ones imply and that imply the original ones. They're therefore an alternate way of expressing the same constraints. The final re-expression of these constraints that we need to do to obtain the standard/most useful equations is a Fourier expansion. Using the normalization conventional for this application, we have the following Fourier coefficients. We can then express the constraints by setting the Fourier coefficients equal to 0, that being mathematically equivalent to setting script p squared and script p bar squared equal to 0, which we already showed. So we finally have these constraints. The last thing we need to do before we calculate the Poisson brackets of these constraints is express the Fourier coefficients in terms of the alpha Fourier coefficients. This will make the constraint Poisson brackets easier to calculate. This can easily be done by simply inserting the alpha-based formulas for the script quantities. For ln, we have this, and the ln bar calculation is essentially identical. With these results, we're finally ready to calculate the all-important constraint Poisson brackets. Inserting the new L operator formulas and simplifying, expanding based on Poisson bracket identities, and then inserting the alpha Poisson bracket relations gives this. Performing the S sum and simplifying gets us here. Seeing as we're summing over all integers from negative infinity to positive infinity, we're free to shift the summed variables in any term. We will take advantage of this in the last term to make the right-hand side factorable. Simplifying then gives us this final answer. The calculation for the L bar operators proceeds almost identically. And finally, the L bar Poisson bracket vanishes pretty trivially. To summarize, we have these Poisson brackets. We can see from these relations that all of these constraints are first class. Ultimately, we can also see from these constraint Poisson brackets that no additional constraints will be generated by demanding that the time evolution of the constraints vanishes. Recall that for this to be the case, the Poisson brackets of all of the constraints with a particular extended Hamiltonian must vanish, where this extended Hamiltonian consists of the normal Hamiltonian plus the known constraints multiplied by arbitrary functions of time. The fact that this Poisson bracket vanishes is apparent from the existing constraint Poisson brackets because the entire extended Hamiltonian can be expressed in terms of the existing constraints. This means that its Poisson bracket with other existing constraints will only generate more existing constraints as per their Poisson bracket relations, which will all just vanish. The only non-obvious part about this is the specific relationship between the nominal Hamiltonian and the existing constraints, which is as follows. To start with, we'll insert the Pn formula into the Hamiltonian expression we obtained previously to get this. We can then use the Kronecker delta to productively re-express it like this. Next, we can insert a useful integral formula for this Kronecker delta into the expression. This Kronecker delta expression then allows the Hamiltonian to be written such that a few familiar quantities show up. Inserting them produces this much reduced expression. If we then recall the script p and the script p bar squares that we calculated earlier, we find this form for the Hamiltonian. If we then apply the L operator definitions, we find this elegant result. So going back to what I said previously, we have nothing but the familiar first-class constraints. Now before we go on to make this theory quantum mechanical, we need to do these same calculations for the open string. It's convenient to be completely done with these classical preparatory calculations before we move on to the next stage. These calculations are so similar to those that we just did, I'll mostly just describe any differences and then state the result to save time and avoid being too repetitive. Let's get started. The differences between the open and the closed string will ultimately precipitate from the different boundary conditions that we derived earlier, instead of the ones we used to enforce the two ends being connected seamlessly in the case of the closed string. We can see that a similar Fourier expansion to that used for the closed string satisfies these new boundary conditions, which is convenient. Keep in mind that some use this alternative convention for defining the Fourier coefficients, and there may therefore be factors of a half to worry about when comparing results from different sources. At this point, we can already see the most important difference between the open and closed string. Because the boundary conditions require x negative n to equal xn, we only have enough variables to construct one independent set of proto-raising and lowering operators like the sets we used for the closed string. Specifically, we usually use this formula, or equivalently this one. Now before we go on with this, for lack of a better time to do this, I will introduce this conventional coordinate extension that can help make some of the math easier. Basically, we go from a sigma range of 0 less than or equal to sigma less than or equal to pi to negative pi less than sigma less than or equal to pi by reflection, meaning this. From this point on, it can be assumed that open string related expressions use this extension unless otherwise indicated. And from here, everything else follows pretty much the same logic we used in the closed string case. To start with, the total canonical momentum is this, and from it we obtain this Poisson bracket relation for the proto-creation and annihilation operators. In terms of these new variables, the equation of motion for x mu becomes this, which of course has this solution. And from that we can construct this expression for x mu, which does turn out to solve the original x mu equation. Now on to the constraints. Recall that we introduced only script p mu at the beginning because we only needed one set of oscillators for the open string. We can also see that script p mu bar is redundant from the perspective of the constraints given the coordinate extension that we made, because script p mu for negative sigma is equal to the formula just given for script p mu bar. As a result, this covers everything in t a b equals 0. Beyond this, everything is the same as with the closed string. Namely, it's useful to re-express this constraint in terms of Fourier coefficients, which satisfy the same Poisson bracket algebra as before, revealing all of these constraints to be first class. Additionally, the same Hamiltonian Poisson bracket argument that we applied in the closed string case allows us to see that there is no additional constraints to be found according to the Dirac method. And now we're ready to actually make this theory quantum mechanical. Nominally, the Dirac method calls for the replacement of all Poisson brackets of Grassmann even quantities with 1 over I h bar times the commutator. In general, we'll set h bar equal to 1. And to adopt physical state conditions that consist of applying the quantized classical constraints to the states. So in our case, these. However, it's been known for a long time that in many theories, these assertions must be modified somewhat to get a working theory. First of all, applying the commutator substitution to all Poisson brackets can lead to inconsistencies due to operator ordering problems, usually requiring some kind of normal ordering, and corresponding subtle alterations to some of the nominal commutation relations to achieve consistency. And second, it has also been known for a long time that the physical state conditions nominally called for by the Dirac method can turn out to be too restrictive to be satisfied by any state. Fixing this naturally means weakening them in some strategic way that allows a satisfactory set of states, but that still implies the usual constraints in the classical limit. Therefore, in practical reality, this part of the Dirac program works out as follows. We first impose the commutator substitution on the fundamental fields in the Lagrangian and their canonical momentum, so in our case these. We take these as correct, only adjusting derivative commutation relations to resolve ordering problems in accordance with some normal ordering scheme. This is necessary to correctly represent the Heisenberg uncertainty principle. We then look for any quantities that contain ordering ambiguities. When we find any, we adopt a normal ordering prescription and calculate their commutation relations directly, rather than assuming the normal Dirac rule can be simply applied to the corresponding Poisson brackets. After that, we must evaluate what states satisfy the naive physical state conditions. If nothing satisfies them, we must consider various alterations of the naive set of constraints until one finds a weaker set that exclusively allows a complete set of physical states, the one exception being that many correct constraint sets let some zero-norm states through. Also, of course, the known classical constraints must hold in the classical limit, or the quantum theory isn't really a quantized version of the original classical theory. A great example of this constraint issue is the group de Bleuler quantization of electrodynamics. Nominally, the Dirac method would call for this constraint, but this one turns out to have no solutions except psi ket equals 0. The constraint that ends up working famously is this one. This alternative can be shown to exclude all of the unphysical states, negative norm states, and longitudinal polarization states, but still admit a complete set of positive norm states. Also, in the classical limit, the original constraint is implied. Both the open and closed bosonic string theories turn out to have these problems. Since we're already working on the open string case, we'll handle that first. Specifically, we'll start with the operator ordering / commutator problem. We can see that there are no ordering ambiguities in the formulas relating x mu and p mu and alpha n mu, so the Dirac commutator rule holds there. You can also easily confirm this directly by calculating. However, we see from this formula that the L operators do have an ordering ambiguity, so the result given directly by the Dirac rule, this, called the Witt algebra, can't be trusted. We therefore need to adopt a suitable normal ordering prescription and then calculate the L operator commutators from the alpha operators, which in turn follow from the fundamental equal time commutation relations that we insist on. The normal ordering prescription that is typically used in string theory is this. If you remember that the creation operators alpha n dagger for a given n are just alpha negative n, you see that this is just the usual normal ordering prescription from quantum field theory. Clearly, this normal ordering prescription only changes anything if m equal to negative n and the operators are not already in the right order because of the Kronecker delta in the alpha operator commutation relations. With the normal ordering prescription established, we're free to calculate the real commutation relations for the L operators and see how they differ from the naive Witt algebra. The easiest way to directly calculate this commutator begins by explicitly writing out the normal ordering. Keep in mind that in all these inequality-based sum limits involving n over 2, any equal to cases only apply when n is even, because of course we're summing over integers. For reasons that will become apparent at the very end, it's useful to derive this formula for L0 from the explicitly normal ordered expression for Ln. Another extremely helpful trick in calculating this is to break up the calculation by first calculating the commutator for Ln with alpha m mu, and then using it to evaluate the commutator for Ln and Lm. First, we insert the explicitly normal ordered formula for Ln, then expand, insert the alpha commutators, and then simplify the Minkowski metric factors with index juggling. The quantities under the two sums are now manifestly identical, and the sums can be combined. Completing the sums using the Kronecker deltas and then combining like terms then leaves us with this final answer. Now we can apply this to the calculation of the Ln and Lm commutator. First, we insert the explicitly normal ordered expression for Lm and then expand out the commutator. We can then apply the commutator that we just derived to yield this, which I will call equation 1 for future reference. At this point, it's clear that as long as m is not equal to negative n, all of the alpha operators commute, given the Kronecker delta in their commutation relations. Therefore, for this case, we can straightforwardly reorder the operators such that the sums can be recombined. It doesn't really matter if we reintroduce the normal ordering notation after recombining these sums, because this is all for the case of m not equal to negative n, which excludes all the cases which have an ordering ambiguity. However, I will introduce it in the last step just to make contact with the exact operator definition of Ln that we're using. The next step in the calculation is to shift indices in the second infinite sum and then combine like terms. Next, we'll handle the case where m does equal negative n. We can actually just take the case of n greater than 0, n less than 0 cases are just the negative of the positive cases that we'll be calculating given the antisymmetric nature of the commutator, and we'll see that this is automatically covered by the result that we get from n greater than 0. We'll also see that the n equal to 0 case, where the commutator should be 0, is also automatically covered by the formula we find for the n greater than 0 case. Anyway, in this case, the alpha operators in equation 1 don't commute and must be normal ordered more carefully. First, it's useful to split up the sums and then flip the sign on the summed index in the first two sums. Next, we can shift the indices in the middle two sums and then re-express the summation limits to get this. We can then split the second term into two terms. Now the first two terms combined. Next, we can transfer the k equal to negative n over 2 term from the last term to the second one, and then split the last term into two and combine the third and fourth terms. Now, to get the whole thing normal ordered, the only terms that need commutation are the lower halves of the second and fourth terms. First, flipping the sign on the sum indices yields this. Now we'll actually do the commutation using the alpha operator commutation relation. Simplifying then produces this. Entering the highlighted sum into the website Wolfram Alpha gave me this result for n equal to any integer, even or odd. We can therefore refactor the quantity in the big parentheses as follows. Inserting this into the expression we've been manipulating gets us this. We can then insert this whole thing back into our commutator. Next, splitting up the fourth and fifth sums gets us this, where the highlighting is for the next step. We can then combine the highlighted terms according to their highlighting, where the new highlighting is again for the next step. And then we can again combine the highlighted terms. We can now see that the middle terms are identical, so we can combine them to get this. Now recall this identity, which we derived at the beginning of this calculation. Inserting it gives us this final result. If we now combine this result with our result for the other cases, we find this grand complete result. This algebra is called the Virasoro algebra, and the constant term, which causes it to differ from the Witt algebra, is called the central term. Ln are called the Virasoro generators. We see that the Dirac rule couldn't be consistently applied to the L operator Poisson bracket because of the ordering ambiguity and its resolution with normal ordering. With the Ln commutator sorted, the next job is to handle the constraints in the quantum theory. Remember, naively, we would expect this. However, we can quickly see that this is too restrictive. Notice that imposing this constraint for a given positive n and its negative at the same time implies this, given the truth of the Virasoro algebra. Therefore, doing this for two values of n, where one is not negative 1, 1, or 0, implies that ket psi equals 0. This leaves us with only two options. Both options include this part, but beyond that, we could either select this, which also implies that L naught on ket psi equals 0, or this. To start figuring out what to pick, we must consider the particle content of the different options. Doing this, however, requires us to do some setup first. The needed setup involves finding a position representation for our as-yet abstract commutator-defined operators. Starting with the fundamental equal-time commutation relations, we see that they can be satisfied by these differential/functional operators. We can translate this to the Fourier coefficients and ultimately the alpha operators using the chain rule and this identity. Specifically, that works out as follows. We can then find a formula for the alpha operators by inserting this result into the script p-mu formula. It's easy to check that these do satisfy the already stated alpha operator commutation relations. Now, remembering our formula from above, we find that Pn mu equals minus I times the corresponding partial derivative. Our new formula for alpha n mu, of course, also implies this form for capital Pn mu, which in turn implies this quantization for the total canonical momentum and the center of mass coordinates. With these differential operators in mind, we can easily generalize the usual Gaussian and Hermite polynomial-based solutions of the simple quantum harmonic oscillator to the case of the infinite set of them that describes the open string. To start with, we know that the annihilation operators are the alpha operators for positive n, therefore the vacuum or vibrational ground state must therefore satisfy this. However, this still leaves the action of alpha naught mu on the vacuum undefined. Given the relationship between alpha naught mu and the total string momentum, and the fact that a free string must be a total momentum eigenstate, even in its ground vibrational state, there is only one consistent way to define this, which leaves us with this complete vacuum definition. The free string must be a total momentum eigenstate because the string must move with a specific total momentum in the vacuum, i.e. be a total momentum eigenstate, where of course the harmonic oscillators purely describe the vibrations of the string. Given the alpha n formula that we have, this equation is easily solved by this Gaussian function. Note that the constant c here carries the dependence on x naught mu that the vacuum wave function requires to satisfy the alpha naught mu part of the ground state definition. Specifically, we have that c is proportional to this, given the differential form that we found for the capital P mu operator. And in exactly the same fashion with the simple harmonic oscillator, we can apply the raising operators to find the wave functions for the higher states. In the simple quantum harmonic oscillator case, these simply work out to be the same Gaussian multiplied by the Hermite polynomials. Since the differential alpha negative n operators in the vacuum wave function have the same mathematical form, barring different constants, we can see that the same result applies here for every level n, meaning that we get a set of Hermite polynomials for every n. This is a useful fact because a basic theorem about Hermite polynomials tells us that any function can be linearly expanded in terms of a complete set of them. Nominally, this means that any function of a given xn mu can be expanded in terms of Hermite polynomials. However, any functional of the string Minkowski space coordinate x mu, a wave functional for example, is just a function of the various xn mu's, and can therefore be expanded in terms of Hermite polynomials or equivalently raising operators applied to the vacuum state wave function. There is, however, one caveat to this last statement. There is no set of raising and lowering operators associated with x naught mu. This expansion in terms of raising operators on the vacuum therefore can't handle wave functional dependence on the zero mode / center of mass coordinates. We're therefore forced to treat dependence on the zero mode separately from dependence on the other xn mu's. Specifically, when we expand the dependence on the other modes in terms of the raising operators on the vacuum, we must let the coefficients carry arbitrary dependence on x naught. Using conventional notation, we have this. We can now actually apply the physical state condition options to this expansion and see what we can learn. When we do this, we'll assume no x naught dependence and psi naught to simplify the calculation. This is acceptable because it's equivalent to the case of zero overall string momentum, and the overall momentum of the string has no effect on its vibrational state. We will start by applying this constraint. For the lowest level terms, the calculation proceeds as follows. First, recall this formula for L naught, which we will apply to this starting point, ignoring terms that clearly annihilate, performing some commutations, ignoring some more terms that annihilate, and finally simplifying gets us this. We can now read off the following equations. Now for the L1 on ket psi equals 0 constraint. For this one, it's useful to prove this formula. From here, the calculation is essentially the same as the last one. We begin with this starting point, ignoring terms that annihilate, commuting some terms, ignoring some more terms that annihilate again, and simplifying yields this. Next, simplifying further, partly based on the fact that H gamma delta is symmetric, produces this. This then implies these equations. Now for the constraint L2 on ket psi equals 0. Similar to before, it's useful to prove a new formula for L2. The first part of that derivation is straightforward. The only less obvious trick is that it's useful to shift the second sum index. Simplifying then gives this. And then applying this formula to understand the L2 constraint works just like before. All higher Ln pass through these lowest terms and annihilate the vacuum. And now for the other selection we could have made. To start with, L-1 on psi equaling 0 implies that L0 on psi equals 0, and we can get the L0 equations by setting A equal to 0 and the L0 plus A results that we just obtained. Specifically, we get these. Additionally, the L-1 constraint itself must be studied. In doing this, like before, we'll find a similar re-expression of L-1 useful. Now we can proceed as we did before. Brief inspection of our result reveals that this constraint is only satisfied if phi is a constant and the other fields are 0. And given how we've just seen L-1 behave on the lowest state, we also see that this pattern will continue all the way down the expansion, requiring the higher fields to be 0. From this we can see that the L-1 on psi equals 0 option can't yield a physical theory, and we're therefore left with the L0 plus A on psi equals 0 option. This, however, still doesn't tell us what A should be. It turns out that there's actually a theorem on this, specifically this theorem. It's in proving this theorem that we see why A must equal -1. Regardless, if we insert that fact, we get these equations. From this, we can see that phi describes a tachyon, A gamma 1 describes a massless vector particle, A gamma 2 describes a massive one, and H gamma delta describes a graviton, the traceless part of gamma delta, and a massless scalar, the trace of gamma delta. Now let's consider for a moment A gamma 1 as an example. Given the constraints, its term in the wave functional accounts for the possible presence of a massless vector boson in an arbitrary string state. It can therefore be thought of as the wave function of a string vibrating as a massless vector boson. This same idea applies to each term. Additionally, the tachyon may seem like an issue, however, this isn't necessarily the case. The presence of a tachyon has long been suspected to indicate that the theory is expanded around the wrong vacuum, an unstable vacuum, much like in the standard model with the Higgs field. Beyond this, it's straightforward to see via the same process that all higher levels constitute an infinite set of massive states. This theorem is also where we get our first inkling that 26 dimensions is special in bosonic string theory. As it happens, there are also problems with taking D to be less than 26 because of an issue in the interacting theory. Unfortunately, I don't think it's reasonable to include the proof of the theorem that I cited just a little bit ago, or the D less than 26 problem in the interacting theory in this video due to length and complexity. A better way to organize my presentation of all of this is to include these topics in separate videos, which I'll hopefully do at some point. Next, we can re-express the Hamiltonian in terms of the raising and lowering operators. We'll start with the expression we found at the beginning. It helps to break up the sum like this. Then we need these substitutions. Inserting these and simplifying gets us our final expression. We see that it takes on the familiar form for a harmonic oscillator. Now the one last thing I want to do before we move on to the closed string is compute the total momentum and the angular momentum for future use. While we've calculated the canonical momentum already, we haven't addressed the mechanical momentum, and we haven't addressed angular momentum at all. The mechanical momentum will turn out to be the same as the canonical momentum in this case, so I will use the same notation for it, but we of course couldn't just assume that. To do this calculation, we'll use the trick of making the infinitesimal transformation parameter local, and then extracting minus the coefficient of the parameter derivative as the conserved current. For translations, we have this. The total momentum therefore works out to be this. This is, of course, obviously equal to the total canonical momentum as mentioned. Using the previously introduced normal ordering prescription, the angular momentum in terms of the alpha operators works out as follows. First, we can conveniently introduce the script p quantity, then applying the range extension simplifies it considerably. We can then easily express it in terms of the Fourier components. Next, we can apply the same reparameterization that we used in the Hamiltonian calculation. Inserting it and simplifying gets us this. Normal ordering and simplifying again then yields our final answer. And with this, we're done with our treatment of the open string for this video. Now on to the closed string. The treatment of the closed quantum string is extremely similar. The derivations and conclusions follow essentially the same logic/process for the open string. I will therefore present the quantum closed string by more or less listing the closed string results analogous to the open string results that we worked out in detail, taking time only to provide logical motivation behind any differences. This is much like what I did for the classical presentation of the open string after I'd gone into detail for the closed string case. To start with, the closed string, of course, uses the same equal time commutation relations, and just as with the open string, this leads to these alpha operator commutation relations. The same normal ordering prescription is used in the closed string case for both sets of alpha operators as with the open string case. This normal ordering modifies the naive constraint operator algebra in exactly the same way as with the open string, giving us this. For the closed string case, we have an analogous physical state theorem that specifies these constraints. The last constraint has a convenient interpretation. To see this, we must first perform some manipulations. Expressing it in integral form, we find this. Inserting the formula for the script p's and multiplying it out gets us this. If we simplify and then make these substitutions, we find this final expression. L0 minus L0 bar therefore produces sigma translations, and the physical state condition that on psi equals 0 requires that all points along the string are the same, meaning that there are none with special properties. We must now explore the content of these constraints by applying them to the arbitrary closed string functional. As it happens, the L0 minus L0 bar condition sets all the fields not associated with a matching set of barred and unbarred creation operators equal to 0. In fact, we can see that this constraint contains no x0 mu derivatives in it at all, but instead just counts the alpha and alpha bar levels and mandates that the difference vanishes. In short, it enforces a level matching rule at all levels. For the phi and h mu nu fields, which are the only ones at the lowest levels multiplying states that satisfy the level matching rule, the other constraints produce these equations. We see that we have a tachyon at level 0 and a massless rank 2 tensor field. In the case of an unoriented string, which has sigma sign flip symmetry, we can see from this equation that we derived earlier that alpha n and alpha n bar must be interchangeable, making h mu nu symmetric. It therefore describes a graviton, the traceless part of h mu nu, and a massless scalar, the trace of h mu nu. However, an oriented string does not have this restriction. In this case, h mu nu can be seen as describing a graviton, the traceless part of h mu nu, a massless scalar, the trace of h mu nu, and a rank 2 antisymmetric gauge particle, the antisymmetric part of h mu nu. From here, it's again straightforward to see, via the same process, that all higher levels constitute an infinite set of massive states. Next, we can rewrite the Hamiltonian in terms of the raising and lowering operators, a calculation which proceeds essentially just like the open string case. We can see that it also takes on the familiar form of a harmonic oscillator. We also have this expression for the total mechanical momentum. This calculation is even easier than the open string case because we don't have to worry about a range extension. However, I still wrote it out just to guarantee that there's no confusion. This result could be simplified further using this relation. Doing so, of course, just shows that the total canonical and total mechanical momentum are in fact equal. And finally, we get this expression for the angular momentum. Again, this calculation is arguably more straightforward to complete than the open string case because we don't have to worry about that range extension step. And this completes our treatment of the closed string for this video, which means we're done. However, before I end this video, I wanted to note that much of this treatment was roughly based on chapters 2 and 3 in Peter West's Introduction to Strings and Brains. Now at the end here, I'm going to leave you with this summary of our quantum bosonic string results.